Okay, so let's look at this question. So we have two masses A and B, and we know that any two masses in the universe attract each other with gravitational force. So the gravitational force between A and B is F. So if we double both the masses, okay, so let's say we have M1 and M2. Now we double the masses, and then we also double the separation. Okay, so here we have distance d, and we double the separation. Okay, it's not here, but somewhere here. So how will that change the force? So we are doubling the masses, both the masses, and also doubling the distance. Well, now the new force be 16F, 8F, 4F, F over 4. So what would be your answer? Let's think about that. So we have two laws for attraction. One is attractive force is proportional to the product of masses. Okay. So if you double this, that doubles the force, and you also double the second one, then that will quadruple the force. Okay. So with doubling both the masses, our force will be now quadrupled. And we have this law also, F is inversely proportional to 1 over d squared. Okay, let's see. So someone answered D. Okay, let's see if that is right or not. So this is due to the increase in the mass, doubling the masses. So doubling the masses quadruples the force. Okay. And when you double the distance, what happens to the force? This is inverse squared law, so it would be 1 over 2 squared. Okay. When you double the distance, that will reduce the force to 1/4. So doubling each of the masses quadruples the force, but doubling the distance reduces it to 1/4. That means the effect would be same. Okay, so that means it would remain same. The force won't change. In other words, the increase in force due to the increase in mass is compensated by increase in the distance. So this one reduces the force, this one increases the force, and the net effect is no increase in force. So that's the right answer, D. Force will remain same. So let's look at this one. Again, two masses, M, small m, and big M, and they are distance r apart, and the magnitude of the gravitational force on each one is F. So F is the force between the two. Now the masses are changed to 2m and 2m. So when you double this and double this, so that will increase the force to 4 times F. Okay. So doubling that and doubling that, you get 4F, and the distance is changed to 4R. So how will this force be changed when you quadruple the distance? So the force would be what? 8? E? So you're answering that one. Now I'm just asking you, if you quadruple the distance, what happens to the force? We'll come to the answer in a second, but I just want to know what happens to the force. Yeah, that's right. So the force would be 1/16. Okay. Oops. Why it's doing that? 1/16 F. So this is due to the increase in masses, and this is due to the increase in the distance, and the net would be 4 times 1/16 is what is that? 4, right? So it will be F over 4. So the net effect would be, the force would be reduced to 1/4. Okay. That's 1/16. Does that make sense? Increasing masses quadruples the force, increasing distance. In this case, in this particular case, reduces the force by 1/16. So, and the net effect would be 4 times 1/16 is 1/4. Okay. So the force would be 1/4 that of the original force. Okay. Let's look at the next one. When an object moves in a uniform circular motion, so you have an object moving in uniform circular motion, that's the direction of the velocity. Okay, at each point the velocity is tangent to that circle. Okay, so the velocity is tangent to the circle. So then what can you say about the acceleration, the direction of acceleration? Is the direction of acceleration same as the direction of velocity, or is it opposite to the direction of the velocity? Is directly towards the center of its circular path? Is directly away from the center of the circular path? Depends on the speed. Yeah, that's right. And what else besides this, what else can you say about the direction of acceleration? Another point also you can mention here, this is the direction of acceleration, and acceleration and velocity are always perpendicular. Okay, so no matter where you see, let's say you see at this point, that will be the acceleration, direction of acceleration, and that's the velocity. So they are 90 degrees. If you look at this point, that's the acceleration, that's the velocity. Okay, so that's 90 degrees. So V and A are always perpendicular when object moves in a circular path. Okay. So that's that. Let's look at next one. We have 3 springs, and for each of the springs the graph is shown by A, B and C. So which spring has the largest spring constant? You should know this from the lab we did last time. Yeah, so steeper this curve, more is K. Okay, K K is greatest for A and K is the least for C. Okay, so we already did that. Okay, so let's talk a little bit more about the springs. So when you stretch a spring, you saw that within certain region it obeys the linear relationship. Okay, what that means is if you double the length, the spring force also doubles. If you triple the length, the spring force also triples. If you quadruple the length, spring force also quadruples. So there is linear relationship between the spring force and the extension, which we call Hooke's law. Okay, that's what we saw in the lab, and that is true only up to a certain point. Okay, so from this point to that point, you get this linear relationship between distance and spring force, but after that particular point, now you won't get linear relationship. Okay, it won't be like if you double the length, then force also doubles. So there is no linear relationship here. Okay, so that means here the spring does not obey Hooke's law. It obeys Hooke's law only along this linear path, along linear portion of the graph. So that's why it's called linear region, and this nonlinear region is called elastic region. Okay. So beyond that point, you will get this kind of elastic region, and if you let go of the spring up to that point, the spring can still go back to its original length. Okay. You will still get the same spring back if you just remove the force up to this point. But beyond this point, if you increase the force more and more, then what you will see is the spring won't go back to its original state. Okay, the spring would be deformed. Beyond this point, you will get the spring or any kind of object, it could be rod or wires, it would be permanently deformed. And then if you further increase the force, at some point the spring or the wires or any kind of rod will break. Okay, so this point is called breaking point. So you start applying force, you see linear relationship, and then after a certain point you will see nonlinear relationship, and then there would be permanent deformation of the object, and then at some point it will break. Okay, so this is the maximum force the object or the wire can withstand. So maximum force a spring or a wire or any kind of like metal, okay, or a rod can withstand. And this force, this maximum force, is called tensile strength. Tensile strength. Okay. So tensile strength is ratio of maximum force. Actually, it's not a force, but it's the maximum force over area. Okay. So this point, at that point it breaks, the object breaks, but the force at that point is called just the maximum force, and if you divide that force by area, then that's called tensile strength. So tensile strength is maximum force over area. So here are some of the tensile strengths of different materials. So steel has the highest tensile strength. It is 1000 times 10 to 6 Newton meters squared. Okay. So if you apply, what that means is, let's say you have a cross section area, a steel rod with cross section area of 1 meter squared. Okay. So to break this steel rod that has the cross section area of 1 meter squared, how much force you need? You need force greater than 1, 2, 3, 1, 2, 3, 4, 5, 6, that much force. Okay, you need force greater than that to break a steel rod of 1 meter squared. So that's the tensile strength. Same thing with here, like aluminum. So to break aluminum rod that has the area of 1 meter squared cross section, you need greater than 450 times 10 to 6 Newton force. Okay. So that is what tensile strength is. So let's see some of the values of tensile strength for biological materials. So these are some of the bones in our body. Okay, cancellous bone has 5 times 10 to 6 Newton meters squared. Okay. Cortical bone has that. You see here the spider silk, okay, has same tensile strength as that of a steel, that of the steel. See how strong the spider silk is. Although it's very, very thin, but if you stack all these thin spider silk and then make like a 1 meter square cross section area, then you will need that much force to break that spider silk. So it's very, very strong. Okay. So let's see. Let's continue our worksheet. So we were working on number 5. So let's look at number 5. A vertical steel beam in a building supports a load of 6 times 10 to 4 Newton. The length of the beam is 4 meters and its cross-sectional area is 8 times 10 to negative 3rd meters squared. Find the distance the beam is compressed along its length. So we are talking here about steel. So we have force and cross section area. With that we can find stress. Okay, so this is number 5. Stress is equal to force over area. Force here is the load, which is 6 times 10 to 4 Newton. Cross section area of the beam is 8 times 10 to negative 3rd meters squared. So that will give us stress. Let's see if I have a number for that. Okay, I don't have answer for that. So you get a number. What do you get? You get some value here. And then we want to find delta L, okay, and we are given L. So strain is defined as delta L over L. Okay, delta L is not known, but L is given. L is 4 meters. So, and then we know the relationship between stress and strain. So, Young's modulus is defined as stress over strain, and the question doesn't give us the Young's modulus, but we can find that from our book. Okay, so the Young's modulus for steel is, let's look at the value from the table. Did I mention that somewhere? I think last time I showed the table, but I don't have the value here. So we can actually, I mean, we can always find that from our book, or you can Google that. Okay, so Young's modulus for steel. Okay, let's Google that. So I didn't bring my book, so so let's see someone. Should we get a big number for stress? Yes. So we get big number for stress because you need lots of force to change the length of a steel rod. So yeah, that's fine. So that's the force you need. So it's 75 and how many zeros? 1, 2, 3, 4, 5 zeros. Yeah. So that means you need lots of force to stretch the rod. Can you guys find the Young's modulus for? Yeah, so please write the number in scientific notation. So whenever you have big numbers, write them in scientific unit. So if you guys have a textbook, please find this Young's modulus for steel. It's given in a different kind of unit, so I want SI unit. So in engineering, they use different kinds of units for Young's modulus, but here we use in Newton per meter squared. So if you guys have a textbook, please look at the value of Young's modulus for steel. Do you guys find the answer value? Okay, so it's 2 times 10 to 11. 2 times 10 to 11. So Young's modulus for steel is 2 times 10 to 11 Newton per meter squared. So we know the Young's modulus, 2 times 10 to 11 Newton per meter squared. We found the stress, so stress is 7.5 times 10 to, is it 6? 10 to 6 Newton per meter squared. Okay, so 7.5 times 10 to 6 Newton per meter squared over strain. Strain is delta L over L. 4 meters. So everything here is known except delta L, so you can find delta L. Okay, so 2 times 10 to 11 is equal to 7.5 times 10 to 6. This 4 goes on the top here, times 4, and then you can take this delta L on this side and then divide both sides by 2 times 10 to 11. That cancel. So delta L would be 7.5 times 10 to 6 times 4 over 2 times 10 to 11, okay, meters. So you can find that out using a calculator. And then number B, part B, what is the maximum load in Newton could the steel beam support before failing? Okay, before failing means we are talking about tensile strength. So tensile strength is the ultimate strength of the material. So we can write tensile strength is equal to maximum force it can withstand over area. Now this one, tensile strength, you need to find it from the textbook, okay, again. So I think I have that on my PowerPoint. So the tensile strength of steel is 1000 times 10 to 6. So this is 1000 times 10 to 6 Newton per meter squared. And then force maximum is what we want to find. And then the area of the beam is 8 times 10 to 3 meter squared. Okay, so this is from standard. That's the standard value from textbook. Okay, this one also. That's also the Young's modulus from textbook or Google. This is tensile strength. And then you can get F max by doing the math there. So 1000 times 10 to 6 Newton meter squared, Newton per meter squared times 8 times 10 to negative third meter squared. Okay, so when you do the math, what you get? So that's 8000 times 10 to third Newton, and that could be written as 8.0 times 10 to 6 Newton. Okay, so the beam can withstand this much force before it breaks. Okay. So far we talked about stretching or compressing of one-dimensional material like wires or rods, but sometimes we may also come across deformation in 2-dimension or 3-dimension. Okay, so what I mean is, if you have a big stack of book or something, okay, if you push it down and in the forward direction, you press it down as well as in forward direction, what will happen is it will deform in this way. Okay, so this kind of deformation is called shear deformation. So the one we talked here, like you have a rod or a wire, you apply force, it will be stretched. So if you pull it down, it will be stretched. This kind of deformation is called tensile. If it is one dimension, it is called tensile deformation. deformation. If it is this kind of deformation, okay, it's called shear deformation. So you have a book, you push the book up and in forward direction, it will be shifted like that. And you may also have the case where you have a three-dimensional object, okay, you have a block or something, a block of metal or something, you push the block from all directions. So when you press the block from all directions, you will squeeze the block, okay, inward. So the size of the block would be now changed, or it would be depressed. So this kind of deformation by applying force in all direction is called bulk deformation. So bulk deformation is deformation in 3 dimension in all directions. Shear deformation is deformation in 2 dimension, okay, in length and width, whereas in case of tensile deformation, it's the deformation in 1 direction, only in 1 direction. So question number 6 is about this bulk deformation. Okay, so you are exerting some force. Okay, so you are exerting force over some area, 4.5 times 10 to 7 Newton meters squared. So if you apply that much force on all sides of a 3-dimensional object, what would be the fractional change in volume? Okay, you have, let's say, water in some kind of container. You press water from all sides by applying that force. Okay, 4.5 times 10 to 7 Newton over the area of meter squared. Okay, everywhere same force. So what would be the change in the volume of that water, or the fractional change? So the formula for that is similar to the one we used, but in this case this fractional change is given by, okay, we want to find this fractional change is given by minus 1 over b f over a. Okay. So in case of this bulk deformation, instead of Young's modulus, we use something called bulk modulus. Okay. In 1 dimension we used Young's modulus, but here we use bulk modulus. And this negative sign implies that when you apply force, there is decrease in volume. Okay. So bulk modulus for water. So different materials have different bulk modulus, just like different materials have different Young's modulus. Like for water, bulk modulus for water is what's that? 2.2 times 10 to 9 Newton per meter squared. Okay, that's the value for water. So we can use that value here. So negative 1 over 2.2 times 10 to 9 Newton per meter squared, and then F over A is given, which is 4.5. The force applied over per meter squared area is 4.5 times 10 to 7 Newton per meter squared. Okay. That's that, and that's that. So that gives us a number which is the fractional change in volume. So let's figure that out, what you get. Is it about 2 times 10 to negative 2? So you can write this as 2 over 100. So you can write this in percentage, 2 over 100 times 100%. So that's about negative 2%. Negative 2% means the volume decreases by 2%. So when you apply this force over that area, the volume of the seawater decreases by 2%, its original volume. Okay. Okay, so that's worksheet 11, and that ends our chapter 7. So now let's talk about chapter 8. Chapter 8 is about work, energy, and power. So let's see, someone has a question here. Could we go over number 4? Number 4 from worksheet 11, you mean? Oh, didn't we do number 4 last time? I think we did number 4 last time. So, but let me give you a brief hint, like how you do that. You can watch last time's video also if you missed it. So, what is the stress exerted on the cable and strain produced by the stress? Okay, so stress is, use this formula, force over area, and that gives you the stress. Force is given, area is given, and then strain is delta L over L. Okay, so you are given delta L, delta L is not given, sorry, is not given, but L is given. This is exactly same as number 5. So L is given 1 meter. So to find this, you can find, and to find strain, we know strain is equal to stress over strain is Young's modulus. So strain would be stress over y, okay, rearranging the terms. Strain would be stress, yeah. So you have stress from here, and this y is given. Okay, so use that value and this given y value, you can get strain. So that answers number A. And for B, so you can get strain from here. So use that strain here, and then delta L would be that strain times 1 meter. Okay, so rearranging the terms. So that's how you do that. So try that. If you still have trouble, please let me know. I can help you next time. Okay. Okay, let's talk about work, energy, and power. This is chapter 8. So what is work? Let's talk about work. So in real life, if you are doing some kind of action, whether you are reading a book or sitting on a desk and working on your computer, that's said to be work in actual life, okay, real life. But in physics, work has a particular meaning, okay. So sitting on a desk and working on a computer is not work in physics. So in physics, work is said to be done only if a force produces some displacement. Okay. Let's say you have a wall and you are pushing the wall for a whole day. Okay. You are pushing the wall for a whole day, but the wall doesn't move. That means there is no displacement. Displacement is 0. You are applying huge amount of force. So there is no displacement, that means there is no work, although you are pushing the wall very, very hard. Let's say you are standing holding very heavy object, okay, a big, like this weight for whole day. If you just hold it for whole day, since you are not displacing this, so there is no displacement, that means there is no work. So in order for work to be done, there must be force and there must be displacement. Okay. So force applied on some object, and that produces some displacement, let's say delta x. Then you can say work is being done on the object. So for work, the formula for work is given by force times displacement. Okay. So the actual definition is work is equal to force times displacement delta x times cosine theta. Okay. So work also depends on how you apply the force. So let's say you apply force in this direction, then you get maximum work. If you apply force in, let's say this block is on surface of some table or something, if you apply in this direction, then no work. Okay. You see here, whether you do work or not depends on how you apply the force. Okay. So it depends on angle. Like for example, if you apply force at some angle like that, then the work you get here would be less than the work you get here. Okay. So this gives you maximum work, whereas this gives you less work and this gives you no work. So work depends on how you apply the force. So this theta is angle between the force and the displacement. Okay. So let's say the block is displaced in this direction, and then you pull it this way, force. So this angle is angle theta between delta x and f. For example, if you push the object like that, then this is delta x. So this would be your angle. Okay, so angle theta is the angle between which way you apply the force and which way the block is moving. Okay, let's look at two numerical and two multiple choice questions. Let's see. So work is done in lifting a barbell. How much work is done in lifting a twice as heavy barbell as the same distance? So you have a barbell, okay, and you lift it. So when you lift it from this distance to that distance, you do double amount of work. Okay. Now if you increase the weight of the barbell or double the weight of the barbell, how will that change the work? Yeah, so this is the weight. Keeping this same, if you double this, that doubles the weight, that doubles the work, right? So doubling the weight or force doubles the work. Okay, let's look at this one. You do work when pushing a cart. You push a cart. If you push the cart twice as far with the same constant force. So here you're applying force F and you push it to distance D. So you do work W. Now in the second case, you apply the same force, but now you push it twice as far. So what would be the work? Work is force times D cosine theta. We are keeping this constant, that constant, changing only D. So how will that change W? If you double that, that will be doubled, right? Okay. So the work would be twice as much. So we have a minute left. I think that would be all for today. We'll continue this in the next lecture. And have a great spring break. We'll talk more about this after spring break. And we'll also have our test after spring break. Okay, our second test will be Wednesday after spring break. Quiz, yeah, I can post quiz right after this class. I was trying to reset homework 6 for everyone, but there is a technical difficulty with that. I mean, I cannot reset all at once. That's the problem. So I need to do one at a time, and it's a very tedious thing to do for me. So if you guys want to redo it, you can come and talk with me. Okay, I can reset it for you, because I cannot do like one at a time. Yeah, for quiz, yeah, you can finish before next Monday, maybe. Yeah, you can get some extension.
So the exam's Wednesday after we come back.
Yeah.
Are you going to post a study guide? Or
I will do that sometime this next week over the break.